ITC lunch of the spring semester, although it doesn't look like spring outside, but we promise it will become spring eventually. Right, Bob?
The days are getting longer.
Okay, that's glad. Right. The situation only gets better with time, this time of year. And today we just heard an excellent ITC colloquium by Romain Teyssier, who I hope is here. Yes, he's at the end. And he will speak a little later. He came to us all the way from Switzerland, which actually was a relatively straightforward task last night. And I guess in Switzerland they have as much snow as we do. But they have better chocolate. Actually, Romain told me that one of the important chocolate factories, Lindt, offers chocolates with small defects to the public at no cost. And that's one of the perks of being in Zurich, that you can go to that. So we will start with Olek Sadowski, who used to be a postdoc in our group, but he's now a Pappalardo Fellow at MIT. And he will talk about breaking the Eddington limit. As you can tell, it already made the news. And then we'll hear from Romain from the University of Zurich, and he will talk about his title actually has a question mark: precision cosmology, myth or reality? And we will not give you the answer yet. And then we'll hear from Mazeh, who is actually the CFA colloquium today. He was awarded a prize lectureship in honor of Michael Carr, and he will give a colloquium at 4 p.m. Related to that. But at the lunch he will speak about Johannes and the 7 dwarfs, Kepler detection of low-level Day-Timescale periodic photometric variations in white dwarfs. He's not here yet.
Yes, he's here.
Just arrived. Okay, was speaking with the students until now. And finally, we'll hear from our own Xinyi duo about non-thermal electron acceleration in low Mach number shots. Olek.
Thank you. I'm Olek. I'm just a simple Einstein fellow at MIT.
Oh, no Einstein, sorry.
There is no better way to start this talk than to introduce the Eddington limit itself. So, if we have a central source of light, it exerts radiating pressure force on a gas acting outward. At the same time, there is gravitational force which pulls the gas inward. If we put the two expressions next to each other and balance the forces, then we obtain the limiting luminosity. No isotropically emitting source of light can exceed this luminosity, and at the same time has static atmosphere, or at least inflowing gas. Whenever luminosity exceeds that number, the gas is supposed to outflow. You are supposed to have a wind instead of an atmosphere or inflowing gas. It is sometimes quite useful to introduce not only the Eddington luminosity, but also introduce the Eddington accretion rate. But for that purpose, one has to introduce the efficiency of converting rest mass energy into the luminosity. And a reasonable choice is to take the efficiency corresponding to a thin accretion disk with non-rotating black hole, roughly 6%. And in this way, we get the following number, which I will refer to as the Eddington accretion rate. What can we break this limit in these limits in case of spherical symmetry? We can't do much with the Eddington luminosity. And this is because it is really a fundamental quantity, which depends only on the opacity. So if the opacity is given, the luminosity is given, this is the limit. But we can play with the Eddington accretion rate, and this is because there is one more degree of freedom, which is the efficiency. So if we manage to decrease the efficiency somehow, to get the low efficiency of converting rest mass energy into the luminosity, then the accretion rate can be very, very large. So this can happen, and one way of taking this place, so that it takes place, is advection of photons. Imagine a spherically symmetric inflow of gas which is quite dense, so it is optically thick. If it is optically thick enough, and if it rushes towards the black hole, with large enough velocity, then the photons will not have enough time to escape. They will be dragged onto the black hole. So this is called advection of photons. And the photons which are generated inside that radius, that critical radius, the trapping radius, will, instead of flowing out, will flow into the black hole, and they will not contribute to the luminosity generated by the source. And ultimately, you can have very high accretion rate. In this plot, it is 10,000 Eddington accretion rates, but the luminosity which is generated by this optically thick flow, which other way would be quite efficient radiator, is well beyond the Eddington the luminosity. So such a accretion can take place, but this is, but that was limited to the spherical symmetry. If we have, if we break the spherical symmetry, we have one more kind of degree of freedom. We broke the axis, we broke the symmetry. So we can imagine, we can now talk about accretion disks, which take place whenever the gas falling onto the black hole has some non-negligible angular momentum. As you remember, the Eddington luminosity, wherever we have a luminosity larger than the Eddington luminosity, there one should expect outflows of gas. But in case of accretion disk, we actually want the gas to inflow only in the bulk of the disk. We do not care too much about the polar region where, when in principle we can have outflowing gas, we can have wind, we can have jets. So it is, in such a case, we may expect that the luminosity cannot exceed, or rather the local flux cannot exceed the Eddington flux inside the bulk of the disk, because the net accretion will be inward, the gas will be falling. We want the gas to fall onto the black hole in this region. But there is no limit on the luminosity in the polar region. In principle, you can exceed Eddington luminosity a lot. This will drive maybe significant wind, but the accretion will still take place near the equatorial plane. This idea is not new. Almost 40 years ago, Bogdan Paczyński and his collaborators already studied the so-called superluminous disks. In this work, they considered a set of equilibrium configurations with which were supposed to resemble accretion disks, which prescribed thickness, and they assumed that such equilibrium tori are supported by radiative pressure. If they are supported by radiative pressure, then the only force that is balancing the effective gravity at the surface is radiative pressure, which depends on the radiative flux. So if you know the effective gravity at the surface, you can get the radiative flux, which balances this gravity, and then you can integrate the radiative flux over the surface of the disk and get the total luminosity. So in this work, they got a formula for some of kind of reasonable reasonable shapes of the disk surface, which, as you see, exceeded the Eddington luminosity quite significantly and had logarithmic dependence on the accretion rate. That was about the total luminosity integrated over the surface of the disk. But what happens in the funnel where there is really no limit on the local Eddington flux that you can get? And that was studied more or less at the same time by Marek Sikora, one of Bogdan Paczyński's collaborators. So he again constructed a disk, a very thick disk, and studied what is the emission, what is the local radiative flux in this funnel region. And he got that this local flux of radiation can exceed the local Eddington flux by dozens, or maybe even reaching a ratio of 100. And that ratio was decreasing quite steeply with the polar angle from the rotation axis. It has been almost 40 years since these works were done, so it is high time to verify them numerically. And this is where I come in. I will be using, for this purpose, my own code, which solves interaction of radiative field with gas, including magnetic fields, in general relativity, in global context, and which uses the M1 closure scheme to close the radiative equations of radiative evolution. This is the setup of this short project. I simulated 3 accretion disks. They all start with roughly with the same torus, equilibrium torus, threaded by magnetic field, but with different densities. And the different densities led to different accretion rates. For all the runs, the spin of the black hole was set to 0, and that was done for the purpose of completely turning off the Blandford-Znaik process, which extracts rotational energy of the black hole, and which is responsible for the regular relativistic jets. In this way, setting it to 0, and by setting the magnetic field to as far from dipolar configuration as possible, we hope to get jets which are, we hope to get jets to get emission in the polar region coming only from the radiation. This will be only radiative jets, not the relativistic Blandford-Znaik jets as known in the literature. And the three simulations led to accretion rates spanning quite large range of radii. And this is what one of them looked like. Left-hand side part of the plot shows the radiative flux. The right-hand side shows the flux of mass, so the local accretion rate. The most important part for our purpose is the left part. You see that quite a large amount of radiation escapes from the innermost region, which is turbulent, which dissipates energy into the funnel along the axis and escapes in quite a narrow angle. Now when you imagine yourself sitting here, you can imagine that a huge amount of radiative flux will be crossing your location, and the source will seem to be very bright. If you happen to sit somewhere over there, there's hardly any radiation, and your source is not bright at all, it's very weak. The purpose of this project is to study the properties of this radiative jet, or in more general context, this jet-like region close to the polar axis. For this purpose, we integrate the data over time and find the average structure. This is the structure of the density. You see that this polar region has the lowest density. That makes perfect sense. As you know, radiation photons try to follow local gradient of optical depth, so they simply slowly diffuse into the polar region, sum up, and escape along the axis. And this is the location of the actual photosphere measured as from the outer boundary down to the center. Only the lowest accretion rate considered had the photosphere inside the domain. The accretion rate, higher accretion rates were quite optically thick up to the boundary. This is what the energy flux in this funnel region looks like. So we define we adopt some definition of this jet region basing on local Bernoulli number, and then we integrate the fluxes in this region and see what are the forms of energy that flows into this funnel. And this is the fractional contribution of different forms of energy. This is the radiative energy, this is the kinetic energy, and this is magnetic. So we see that in the innermost region, where the radiation escapes from the disk, from the most hot part of the disk, this is the radiative flux which dominates. But as you may remember, this funnel is, for such high accretion rate, is optically thick, so this radiation still interacts with the gas. If it was optically thin, then the radiation would simply escape, and this is the end of the story. But because of the fact that there is still significant interaction between the gas and the radiation, the radiative energy, the energy is converted into kinetic energy, and the gas accelerates, and this is reflected in the bottom plot, showing the velocity of the gas along the vertical coordinate. But at the point where the radiative flux and the gas crosses the photosphere, the interaction becomes negligible. The gas no longer is accelerated, and we reach the regime where the whole jet region is dominated by the kinetic energy. And this kinetic energy later on will dissipate, because this is not a laminar flow. It will dissipate and hopefully create radiation, which will be observed. And this is the money plot of this talk. This is the luminosity inferred by an observer looking at given polar angle near to the axis, close to the axis at the central source. These are the luminosities for different accretion rates and for different polar angle. And we see that this local flux of radiation can exceed the Eddington flux by hundreds, even thousands, if the accretion rate is large. If the mass of the black hole is large, we can get also enormous amounts of energy. So this is the amount of energy, this is the luminosity that the source pretends to be for an observer looking along the axis. And the summary, the takeaway message is that supercritical accretion is feasible if only there is enough mass close to the black hole. If that mass gets there, it's an open question. But if it gets there, then the thickness of the disk collimates the radiation along the axis, and the source is the brightest if you happen to look along the axis. And in this region, the super Eddington luminosities, or rather super Eddington fluxes, are really not a problem. And this type of configuration can be important in context of your ultraluminous X-ray sources. In this way, you can get huge luminosities, even for quite low masses of the black holes. But it also can be relevant in context of tidal disruption events when we have high accretion rates on the onset of the accreting phase. That's all. Thank you. Well, I would say that in this type of simulations, which are 2 or 3 dimensional, it's treated kind of self-consistently, so it should be taken into account. It was an issue for the Polish donuts, which are really analytical, and it was a fixed gas structure, and on the top of it, the radiation was evolved or analyzed. But here we solved them, we coupled them, so it should be all fine.
That does not ruin the funnel.
No, definitely not. It is still open.
So we saw in Romain's talk earlier today that if you have converging beams with the M1 closure relation, which will get spurious beams that are directed sort of perpendicular to their direction. Is that a concern for you in these calculations?
It is not a big concern in the context of this funnel, because you can imagine that the radiation that actually contributes to the radiation flux in the funnel comes from kind of a conical surface. And these are not discrete sources of light. This is a conical surface, so there are no beams overlapping with each other. There's like a continuous emission overlapping. And what is important in this context is that these beams which come from this conical surface, they overlap, yes, and maybe they overlap in a wrong way, but the vertical component of the radiative flux will be conserved, because M1 closure conserves momentum and energy. So once they overlap, maybe they will not overlap properly, but they will definitely produce the proper vertical radiative flux. And this is the vertical component which is responsible for the acceleration, and which is the one which we measure. So it should be fine.
For the synchrotron emission, you've got accelerated charged particles. Where's the mass loading happening here? How are you determining where the particles are accelerating?
So once again, the gas is evolved together with radiation. So at every time step there is kind of radiative force acting on a piece of gas, which is in the domain. So that gas kind of enters this polar region because it is in part driven by radiation, which tries to go into that direction, so it pushes the gas away. On the other hand, we may have winds driven by magnetic fields, like Blandford-Payne winds. So there is a couple of mechanisms which can drive the gas into this funnel region. And once it is there, it feels even more and more radiative acceleration. So it's consistently solved, radiation with the gas, and this is this like configuration that is the equilibrium configuration for this type of accretion.
I was just going to ask a question about neutron stars. So this formalism that you developed tends at least in part on theory of a black hole, but as you know, recently gamma ray studies by Jeremy seem to find that one of the ULXs is very likely to be a neutron star. So I was just going to comment about what would happen in your formalism if you had a neutron star.
I would say that not too much would happen. As long as the magnetic field of the neutron star is relatively weak, the structure of the supercritical flow, quite far from the horizon, should be really very similar. The number that would change would be probably the net efficiency of the flow. It is quite likely that neutron stars, because of the surface, extract more energy from the flow than black holes. So it may be by a factor of a couple even brighter. But this still holds. I'm very interested in simulating a similar setup with a neutron star boundary condition. But my expectation would be that at least the qualitative picture will stay the same. So neutron stars can also be super luminous, if you are lucky to look along the funnel at least. Thank you. It's on.
Can you hear me? Yes? Okay. Okay, so my name is Romain Teyssier. I'm from the University of Zurich. And I want to briefly mention ongoing work in trying to predict the theoretical predictions of the matter power spectrum in large-scale structure formation in the universe to very high accuracy. And I will briefly mention how accurate we need to be. And I will put this in the context of the large-scale galaxy surveys, such as LSST or the upcoming European mission Euclid. And the goal here is to measure galaxy clustering or to measure weak lensing to an exquisite accuracy, and then to use these measurements to infer the cosmological parameters beyond the 1% barrier, which then will maybe allow to us to discover new physics. And so this 1% barrier, this 1% requirement is very important because it's really needed in order to possibly detect new physics beyond the standard model. Actually that's an official requirement from the Euclid mission, is that the theoretical prediction must be better than 1% accurate, up to a scale, physical scale of 10 inverse megaparsec. And what is even scarier is that this must be true including all effects, for example, baryonic effects, which are very hard to model, as you will see. So that's basically what we need to do, and we need to be ready by 2025. I think it's a very hard and ambitious goal. So one way to accomplish this is to use n-body codes, which is the state-of-the-art numerical tool with which you can compute the clustering of dark matter to great accuracy. And this n-body approach is the traditional approach, but still there are a lot of different codes out there. And I give you an example of 3 codes here. Gadget, which is a very popular code based on the tree technique to solve the gravitational interaction at small scales, and the particle mesh technique to solve on large scales. Then you have Ramses, which is the code I'm developing, which is full particle mesh. There is no tree-based approach, except that the mesh is adaptative, so that's what gives you resolution. And then there is a third code called Picadigraph, which is developed in Zurich too, which is a pure tree-based approach. There is no particle mesh approach. So these 3 codes are very different, underlying techniques, but they are all n-body codes, right? So that's the point. So we have done an experiment within this large collaboration, which is to run exactly the same initial condition. Basically, we start with the identical files. And we evolve those initial conditions, which are set at redshift 50, roughly, on very large periodic cosmological boxes, all the way to redshift 0. And then we look at the result. And so what you see here is at different redshift, from top to bottom, the 3 different codes. So each color corresponds to 1 code. The reference here is Ramses, because that's me giving the presentation. But it doesn't mean it's the correct solution, right? And so the green curve is the tree code, and the red curve is gadget. And so what you can see is that there is basically, the x-axis here is the scale, the inverse of the scale, so the k mode. And below 0.2 h over megaparsec, you have what is called the linear scale. So that's where basically everything is predicted more or less using linear theory. And beyond k equal 10, that's the deep nonlinear regime, where basically everything is kind of fuzzy. As you can see, that's also where the code starts to deviate at more than, I would say, 5-10% level. And in between the two, you have this quasi-linear region between 0.2 and 10, which contains a lot of information. So in terms of information content, exploiting those scales in the future galaxy surveys is primordial in order to reach this 1% accuracy. And therefore, we need to be able to predict the power spectrum within this light gray rectangular region you see, which is this 1% barrier. And so that's the current state of the art. So you see that below k equal 1, we reach the requirement. So all these codes with different techniques give the same result within 1% accuracy. But beyond k equal 1, that's not the case. And there are some weird effects, which are sometimes counterintuitive. I don't have time to enter the details here. But basically, we stay below 5%, but we are not below 1%. And so that's something very important to have in mind, that based on this kind of internal calibration approach, n-body codes are not 1% accurate between k equal 1 and k equal 10. So just to put this in a more historical perspective, 10 years ago, a similar exercise was performed, 10 years ago, and the accuracy below k equal 1 was 10%, right? So basically, we improved the situation by a factor of 10 in terms of accuracy, and this means recoding, changing the accuracy of the solvers, and so on and so forth. But now, today, that's where we are. We are basically at 5% below, beyond, between 1 and 10. So there is a traditional way to predict this theoretical power spectrum. It's using this so-called cosmic emulator, which is a mixture of numerical results and analytical results, and which can generate the power spectrum in any cosmology. And this tool is used to fit the data. You need to be able to leave the cosmology as a free parameter and to fit your power spectrum, your theoretical prediction. And so what we did was to compare to this cosmic emulator here, and you see that basically you have another example here from a collaboration here in the US. Basically, we are more at the 2% level compared to this cosmic emulator. And beyond k equal 1, there is a strong bias, a strong discrepancy, which is a bit worrying if one wants to predict below the percent level. So that's the current state of the art, and bear in mind that this is with pure n-body, only dark matter simulations. It's basically the simplest problem you can solve. And that's basically where we are. So now, if you want to go beyond that, I think, one thing that can happen here is that all those codes are wrong. They are consistently wrong. And nobody knows what is the correct answer, right? In the nonlinear regime, we have no idea. So one alternative way to solve this problem is to use a completely different technique, which is not based on n-body, but which is based on Vlasov code or Vlasov solver. And there is this very recent effort, which is a heroic effort, trying to solve this problem of dark matter dynamics using Vlasov code. So I don't have the details. I don't have time to enter the details here, but basically it's an ongoing effort. And in terms of accuracy, so here I've plotted the power spectrum using different numerical techniques within this Vlasov approach. And you see that they are painfully converging. So, they don't have the same level of accuracy than n-body code, of internal accuracy than n-body codes. They are still improving on the numerical techniques, but in, I would say, a couple of years, I think they will be able to reach this percent accuracy, or 10% accuracy, and then it will be very exciting to see if this Vlasov approach is in a disagreement or not with the n-body approach. And actually, we don't know that, right? So I think it's something to have in mind also. Maybe n-body is wrong. Okay, so now, briefly, I move to what we can do beyond this pure n-body dark matter kind of approach. And there is an ongoing effort on in the community to model large-scale structure formation using modified gravity model. And so this is an example using this so-called F-over model, which is basically a modification to GR. And there is this parameter, F over naught, which measures the amplitude of the scalar field that you have to add in the Einstein equation. And you see that depending on how strong the effect is, you can have very large deviation of the measurement up to 50% for very large values for this F over naught parameter. But here is this last plot showing that that's the current constraint on this F over naught parameter. So you see that it's probably of the order of 10 to the minus 5, 10 to the minus 6, using various constraints from solar system experiments or strong length experiments. And if you look at where the prediction lies for 10 to the minus 6, you see that it's at a few percent level, which is of the same order of the systematic errors that we predict for the n-body codes. Right? So here at the theory level, there is a little problem here, which is that this modified gravity model, at least the viable modified gravity model, are quite weak, and they are at the level of the inconsistency of the codes. Okay, so let me briefly mention the baryons. So let me jump over this plot. So the baryons, the main effect of the baryons is to regulate the distribution of gas and stars inside halos. And so, okay, I don't have time to enter the details, but focus on the rightmost plot, which is again the same power spectrum deviation from the standard model. And you see that the effect of baryons is to cause, according to popular theories here, a deficit of power between k equal 1 and k equal 10. And this deficit of power is at the, say, 10% level. And that's the effect, which is, I think, an optimistic effect. Like that's kind of a scenario for which baryons are not doing too much. And so here the key is that although the effect is strong, we have a 10% effect due to baryons. The key here is we need to be able to understand this effect at 1% accuracy. So if the effect can be strong, can be 10 or 20% strong, but if we understand this effect and if we can correct this effect to 1% accuracy, then baryonic effects are under control. And this is the exercise we played here. I'm sorry, I don't have time to enter the details. But basically, there is two scenarios here to fit the cosmological parameter in this forecast of a Euclid mission. One, if we include in our model baryonic effects, then we get all the solid lines here on the right-hand side in the cosmological parameter space. So there is no bias. But if we ignore the baryons, then we have a strong bias that kicks in, and we can have positive detection of dark energy or exotic models just due to the fact that we ignore the fact that baryonic effects can play a role at the 10% level. So I think precision cosmology is possible, but we still have to work quite a lot in order to be ready to reach those very ambitious goals, which are the goal of these large-scale surveys. Thank you. Yes, so this example I took here is based on an analytical model and doesn't capture these effects. So there is a very strong effort modeling those baryonic effects, and the key here, the key physical mechanism that you need to consider is the effect of AGN feedback in order to regulate baryonic physics at the scales of groups and clusters of galaxies. That's what you need to nail down in order to predict this signal. And AGN feedback is is a very tricky business. And so there are a lot of nonlinear effects. For example, if you, with AGN feedback, you push hot gas away, it can have a back reaction on the dark matter, which will then expand. And all those are very subtle, and they are very poorly, I think, known today. Clearly not at the percent level. And so that's why I think the correct strategy in this context of precision cosmology is to consider all these effects as a nuisance, and you need to be able to marginalize over, right? And I'm not saying it's possible, but I'm saying that's the most reasonable strategy, is to be able to marginalized over all these effects, including the nonlinear coupling effects you're mentioning, and then convince ourselves that they are properly marginalized over so that we don't have any bias in the measurement. Yeah.
Thank you very much.
High technology. Okay, I'm very happy to be here, and I would like to tell you about a surprising finding that we had with Johannes, of course, is Johannes Kepler, about white dwarfs that were observed by Kepler. So you all know that Kepler's main goal was not to observe white dwarf, but somehow a few people that were interested in the mainly pulsation of white dwarf convinced the TAC or the committee to include a few white dwarf in Kepler, in the Kepler objects. So you know that Kepler, from the photometry point of view, is amazing and made a real revolution. I'm not talking about the transits, and I will talk in the colloquium about another revolution that Kepler did with regard to find stellar rotation. But also on white dwarf, although the sample is very small, we find a kind of surprising findings that nobody could think before that it's possible to find, and the results are I think interesting. So Kepler observed 14 white dwarfs. These are the list of them. And this is the number of quarters that Kepler observed of them. Quarter is about 3 months. And this is a long cadence, and this is short cadence. In order to detect pulsations of white dwarfs, you need of course, because the pulsations are expected to be very short, so you need short cadence. The long cadence integration time is half an hour, so you are not able to detect pulsations. But what we did is we took the light curves and looked for long-term modulation of the light of the white dwarf, and in a very surprising way we found interesting modulations. So I'll show you a few of them. Here is one of them. You see, this is the light curve. This is a part of the light curve, so you can follow that, and you really see. You don't need to do a special analysis in order to see that this is kind of modulation. And in fact, the modulation turned out to be periodic, with a period of 8 days. This is the period. And this is the data folded with this period, binned. And you can see that there is a modulation of about 800 ppm. 1,000 ppm is 0.1%. So, you know, before that, nobody would be able to dream to detect such things. But in fact, it's getting better and better, because here's another example where if you look at the data, you don't see anything. It's just noise. But if you do just the power spectrum, just the power spectrum, nothing fancy. You get a peak which is huge, and with a half a day, and if you fold the data, you see there's a little bit smaller amplitude of 500 ppm. Of course, your ability to see the modulation depends, of course, on the amplitude, but also on the noise of the data, and that depends on the brightness of the star. White dwarfs are very faint. And we even detected 60 ppm. This is really small. And you can't see anything here, but still it's very significant. So in general, I showed you the table, but I cut the results. So here is the results. Seven of them we didn't find anything, up to, of course, some threshold. But for 7 of them, half of the white dwarfs, we found a significant modulation, quite stable, with periods which range, 10 days. This is quite short, and with modulation of say 100 to 1,000 ppm. So this is new. So what could that be? So we could think of a few possibilities. I will not mention all of them here. I'll show just one graph that summarizes a few possibilities and a few equations that point to another possibility. One type of possibilities is that, obviously I would think of this because I'm coming from binaries and planets, is that this is coming from a binary orbit, that the white dwarf has a companion. Has a companion, but faint companion, of course. Otherwise, we wouldn't see the white dwarf. So it has to be either a planet around white dwarf. That's very interesting, or a brown dwarf, or another a white dwarf. And a companion can produce a periodicity in a few ways. It can reflect the light of the brown dwarf. It can change the intensity of the white dwarf by the famous beaming effect that Aviv was predicting that Kepler will detect, and he did detect in many other cases. And also, if there is a companion, the companion, if it's very faint and doesn't have its own light, can be heated by the light coming from the white dwarf. And then we can see day and night of the companion, which is not really a reflection, but reprocessing of most of the light of the UV, of the white dwarf in the UV, reprocessing it into the Kepler band. So we checked all these cases, whether it can work with these 3 types of effects that can be induced by a companion. And this is the graph that summarized that. These are our 7 dwarfs. And we put some other detection, not necessarily from Kepler. And these are different lines, upper lines, upper limits for the different effects. For example, this one is just reflection. So that reflection depends on the size of the companion. And this is beaming, the beaming effect. The beaming effect is not very sensitive to the period. This is the period in log of days, and this is the amplitude that we detected. So none of the effect can explain all of them. But of course, life can be complicated, and maybe the 7 dwarf are caused by more than one effect. Another possibility, which I like, just because I worked on this in my previous life, of accretion onto white dwarf in cataclysmic variables. So maybe the white dwarf is accreting material from the interstellar medium. And if the white dwarf has a magnetic field, which we believe most of them do, so that magnetic field is funneling the accretion of the matter onto the pole, onto the magnetic pole of the white dwarf. And that will create a hot spot on the pole, on the magnetic pole of the white dwarf. And that will introduce a modulation. So if this is the case, we are not seeing the rotation of a companion, but we are seeing the rotation of the white dwarf itself. That's what we are detecting. So you can play with the equations, and you don't need to assume outrageous numbers for the interstellar medium in order to explain all that. And there are, I think, one or two more options. Oops. So I think it's interesting, and I think it opens a new I don't know if a field, but it's a new subfield of white dwarfs. And just to finish, I would like to just flash a very recent discovery that we did a few weeks ago, and that we discovered a white dwarf. I erased all the signs that can lead to what system is this, because it's not published yet. But we discovered, at this case, a hot star of 8,000 degrees, kind of A star, that has, with a 3-day period, a white dwarf companion. The white dwarf companion causes an eclipse where the white dwarf is going in front of the hot star, but there is an occultation when the white dwarf is going behind the hot star, and by the depth, comparing the depth, you can deduce what is the temperature or the temperature ratio between the hot star and the white dwarf. So the conclusion is that white dwarfs are interesting. Thank you.
Even without accretion, would you expect some activity on the surface of the white dwarf that could increase the cause the modulation, periodic modulation, if there is a region that is hotter than others, magnetically active?
But how can it keep its temperature higher than the? You need some source of energy for this. Maybe.
I don't know what the sensitivity requirements would be, but I can imagine that if these would be observable in the X-ray, you could distinguish between modulation to the funneling.
Absolutely. Absolutely. Well, this is very small modulation, and white dwarfs are faint. This is 10 to the minus 4, and less.
The other thing is,
and it's long period, So it's not that you can observe for 2 hours and see the modulation. You have to go back and get a good zero point in order to compare measurements on different time.
You need at least 10 to the 8 photons to detect the effect. And it's not easy.
but this is one of these things working principles.
Well, it only depends on the size of the telescope.
But the other thing is, with regard to the planet hypothesis, these are very tight orbits.
Yes.
around, is there a credible model for how you get a planet that close to a star that has undergone this, explosion, this release of material?
This reminds me on the question in '95 when Michel Maillot came up with 51 PEG, is a planet with a period of 3.5 days, and everybody says, is there any theory how a planet can come so close to a star? So we don't know. But if a planet can come so close to a star, it can stay there. And on top of that, the white dwarf went through some giant phase where if there is a planet, it went through its envelope, so it could spiral in easily to that period.
I was just curious to go back to the original 7 dwarfs here as to what is the longest timeline on which you have observations? In other words, could you see any changes?
We tried that. You can see by the number of quarters. So usually, for example, this one was observed in quarter 3 and in quarter 10. And quarter 3 and quarter 10, it's 6 between them, 7, so it's about 2 years. So the time span is, the whole Kepler time span was 4 years. So it's not enough. And you have to take into account that because the signal is so faint and so long, your precision on the period is not very high. It's, I would say, 10 to the minus 3, delta P over P. So it's difficult to.
So you can't separate your data 3 years apart and get a useful comparison to see the
I could get an upper limit, but we tried and we didn't see anything significant.
Oh, okay. Oh. So hi everyone, my name is Xinyi and I'm a local graduate student. Today I will be talking about work I've done with Lorenzo and Romain here, both at ITC, on lens-thermal electron acceleration in low Mach number shocks. So just to motivate our study, the observations of radio galaxies at the outskirts of galaxy clusters provides the most convincing observational evidence that electrons are accelerated at low Mach number shocks. And the textbook example is this sausage relic. So here we are seeing a radio image of a galaxy cluster, and at the northern end we see this megaparsec scale radio bright feature, which is produced by the synchrotron emission of accelerated electrons. And we zoom in with X-ray telescope and measure the plasma density across this radio relic. We see that there's a clear temperature jump, which suggests there exists a shock, and that the temperature jump factor suggests the shock is low Mach number. So electron acceleration at low Mach number shocks. So traditionally, particle acceleration has been explained by invoking the first order Fermi acceleration mechanism. The way it works is that particles can be scattered by the magnetic waves that are assumed to exist at both sides of the shock, and they gain energy after each shock crossing because the flows is convergent. And despite the wide successful predictions of this mechanism, it more or less stays as a paradigm in that it ignores the microphysics. For example, you see that it relies on those magnetic waves, but it doesn't provide answer in terms of how do those waves arise. And more importantly, there has been significant challenge in applying the Fermi acceleration mechanism to explain the electron acceleration. Because in order to be injected, for the electrons to be injected into this process, and the previous analytical method has assumed that the electrons has to be scattered by the downstream waves, and in order for them to cross the shock freely, they need very large normal radius. That translates to a very sharp injection momentum requirement. And if you look at the momentum spectrum of thermal electrons here, across this 8th order of magnitude in number density, no electron can reach this high requirement. So that means previously we thought the electron acceleration efficiency is really poor. But on the other hand, we have those concrete observations showing that electrons can be very efficiently accelerated. So in order to understand understand those megaparsec features, we really need to go to the microphysics and to approach this problem from first principles. And we study the electron acceleration in low Mach number shocks. We find the electron Fermi type acceleration, and it's mediated by electron self-generated waves, which gives the answer to where do the waves arise. So to approach this problem, we use the particle in cell method, which simulates a plasma from first principle self-consistently, and we use the massively parallel Tristan MP code, which allows us to achieve large enough box size and long duration to allow us to see first-time electron Fermi acceleration in low Mach number shocks. So here's our simulation setup. So from the right hand of the box, we send in thermal electron proton magnetized plasma, and its flow velocity is parameterized by the Mach number, and the strength of the magnetic field is parameterized by the plasma beta. And a shock will quickly form and then propagate to the right. So for the run I'm showing today, we take the parameters motivated by observation of those radio relics. So low Mach number, high plasma beta. And we even have a polarization measurement to constrain the orientation of the magnetic field with respect to the shock propagation. And so let's see how do the non-thermal electrons emerge in the simulation. So here I'm showing you the density profile of the plasma, and at a very early time the shock has barely formed yet. And I'm zooming in this region, blue box region, to show you the electron phase space in this region. And at the beginning, the electrons are all thermal, and to guide your eye, I'm showing you these white boxes. And as the movie goes, you should see that there are more and more electrons propagating, populating the areas beyond the thermal spread. So these are the non-thermal electrons. And let's look at the movie again, and then zooming in further into this purple box region where I'm focusing on the electron energy spectrum. So as the time goes, we see that there is a clear non-thermal component in the spectrum, and about 10% of the electrons can be efficiently accelerated. And we see that the maximum energy of the electrons are constantly growing with time, which implies that this process is very sustained. So looking at this, the first question we can ask is, how do the electrons gain their energy? So we find that they gain energy through this so-called shock drift acceleration mechanism. And to see how it works, the most intuitive way is to look at the particle, see as it drifts along the shock surface, which is the 0 here, and its energy evolution. So we see that it comes in towards the shock, it stays at the shock surface for a long time, meanwhile it gains a lot of energy. Then it gets reflected in upstream, and so why is this electron drifting along the shock surface? That's because the density compression at the shock gives a gradient of magnetic field. And the grad V force will push the particle to drift along the shock surface. And at the direction of the shock surface, there's a motional electric field. So when the electron is drifting along this direction, it samples the electric field and gains its energy. So now that we know electrons gain energy through this process, we still want to understand why we're seeing this highly efficient acceleration in contrast to previous analytical results. And in order to do that, we really need to see how are the particles injected into this SDA process. And we again utilize the power of a PIC, where we can track a large ensemble of particles. And without going to the details, I'm just going to summarize the results. We found that the electron, in order to be injected into this process, they are mirror reflected at the shock. So in contrast to previous thoughts that that they need to go to downstream and to start with a very large lambda radius. And this mirror reflection is only a requirement on the velocity space of electrons. So it's a much less stringent requirement, which yields much higher electron efficiency. So with this verified injection mechanism, we can actually compute a synthetic energy spectrum of electrons, and we compare it with simulations. And at the early time, we see that it agrees very well with the simulation results. But at later times, if we assume particles go to the shock, go one cycle of SD and go back, as we saw as the first particle, it cannot explain this long-term energy evolution of a lot of electrons. So what is happening here is that the electrons can undergo multiple cycles of SDA, and it's mediated by the upstream waves. So here we're seeing another particle going to sustain the process. It's drifting again along the shock surface, gaining energy. So first cycle of SDA reflected towards the upstream of the shock, and we see those waves slowly developing and propagating into the shock. And by constantly interacting with the waves, the electrons getting pushed back to the shock. So now we see it's getting another cycle of SDA. So this is really, only Pick can tell us this nonlinear evolution of accelerated particles and how they act back on the particles to get further acceleration. So this is just a teaser slide. So we've seen those waves, which is important in sustaining this energy, long-term energy evolution, and we've verified that they're indeed electron self-generated, and we find they're the so-called electron fire hose instability. So that completes the picture of electron acceleration in low Mach number shocks. So thermal electrons move towards the shock. Some of them participate in this SDA process, and they drift along the shock surface, gain energy, and get reflected. In the upstream, there's self-generated waves. Some of them will be scattered back and then enter this loop of sustained acceleration, and some of them go further upstream, but they generate more waves to sustain this electron acceleration cycle. So coming back to our electron injection problem, so before we thought that electrons, in order to be injected, they need to be scattered by the waves and downstream waves, so that they need to start with an extremely high momentum. So it used to predict very low electron acceleration efficiency. But what we found through first principle simulation is that the shock itself can reflect the particles upstream, and it reduced the requirement to a requirement on the velocity space of the electrons, which yields a much larger fraction of them to be accelerated. And so which is why we see about 10% of electrons can enter the non-thermal evolution, and this naturally explains why are we seeing these radio bright features at the outskirts of galaxy clusters, and then bridging the megaparticle observations to the microphysics. And with that, I will conclude my talk. Yeah. Oh.
Quick question, in this injection mechanism, does it depend on the temperature of the plasma is before it gets shocked? In other words, if your Maxwellian is much more shifted.
So we've done like much more simulation to study the parameter dependence, and there is a weak dependence on the temperature of the temperature of the plasma. It's more on the Mach number, and and the obliquity angle also matters, which I didn't have time to talk the dependence here. Yeah.
One quick last question.
So if you have 10% of the electrons which are accelerated to 10 times the thermal energy, it means the energy density in those electrons is the same order of the thermal one.
Yeah, I think if you plot gamma squared, the ND gamma, the non-thermal bump is pretty high.
So it means you should have a back reaction on the flow itself, because you have as much pressure in the non-thermal component that you have in the thermal component.
Well, it is generating those waves that are like that is not exist. That doesn't exist when you initialize it with a thermal plasma.
Most of the fluid energy is still in the protons. Okay, so these are equal number of non-thermal electron energy versus thermal electron energy, but most of the flow energy is still in the protons.
We reached our time limit. Any further discussions?
They will do something, but it's not a... These are ions that are coming by upstream. So 10% of the energy of the ions is 10% of the energy of the flow. This is 10% of the energy of the electron, or like a third fraction of the energy of the electron. It's still a minus fraction of the energy. Most of the energy is in the ions. And Lorenzo, I bothered you on this. We'll talk this afternoon. Excellent. It was very good. You should use better the pointer, especially in the beginning.
I wanted to use this one, then I realized that
it's very heavy.
Yeah, so
especially at the beginning, you were very shaky. So think about it. Yeah, but you won't reach it. You have to go. That was very good. Send me the slide. We'll see you later.
Yeah, be safe.
Yeah.